As I was saying, hi, hello, hello, and hi. My name is Lieutenant Petrie. I am an officer with 781 Air Cadets out of Calgary. I know way too much about aviation and all of this stuff. I taught ground school in Brandon for the 2 years that we had glider there. And meteorology is one of my favorite subjects to teach, so I'm very excited to do this with you all. My pronouns are she, they. And today we are going to be doing about 40 minutes, might be a little more, might be a little less, of 403.01, which is Intro to Meteorology. So for getting started, our main teaching points are talking about the composition of the atmosphere, temperature scales and differences, properties of the atmosphere, and of course our favorite ICAO standards. We'll also be talking about atmospheric pressure and measurements of it, precipitation, humidity, as well as atmospheric heating and cooling. So the goal of this lesson is, of course, to give you a nice basic intro to help you with a foundation for everything else that you're going to learn in meteorology. So I hope that you are excited about this as much as I am. I know that for some people, meteorology is a miss. Some people are just not a fan of Met, and that's okay, but I hope that you guys enjoy this. If you are looking for any references, any reference material or things to use to help you out with your learning, From the Ground Up is always a nice thing to have available, as well as the Air Command Weather Manual. That's something that NAV Canada has, as well as the Transport Canada Study and Reference Guide for Glider. Has some good information about meteorology as well. So before we get started, of course, we're going to be starting with the composition of the atmosphere. So I am going to be using the chat with you guys. I like asking questions. I like knowing what you're at so far for a base. So in the chat, tell me the different levels of the atmosphere. Or you can also raise your hand and I'll call on you and you can unmute yourself. But I want to know what you guys know. Nice, nice. Alrighty, fantastic. Yes, I'm loving this so far. You guys are doing good. So we've got our troposphere, stratosphere, mesosphere, thermosphere. We also have our ionosphere, but we don't talk too much about that. And then there's our exosphere. So there are different things that happen in each of these. So we are going to be going through and talking about those. Sorry, my computer decided it wanted to tell me that it's time for an update, which is wrong and bad timing. So, of course, we are going to start with what is closest to the Earth and go from there. So our first one is our troposphere. So the troposphere starts at Earth's surface and extends 28,000 feet at the poles and 54,000 feet at the equator. It's the densest part of the atmosphere. This is where pretty well all of our weather is in. So especially when we're worrying about our flying, this is going to be kind of our most important level of the atmosphere, especially with glider or private pilot's license. You're not exactly getting to the heights where you're going to be worrying about a lot of the things that the other spheres are doing, but it's good to know. With the troposphere, temperature, pressure, and density rapidly decrease with height. And at the end of that, yes, the top of the troposphere is the tropopause. So very nice. Then we have the stratosphere. So as I'm sure you can guess with most of these, they're going to start just above where the other one ends. So the stratosphere is going to start just above the troposphere, and it extends up to 50,000 feet above the troposphere. The ozone layer is in this as well. So if you're ever hearing about the ozone layer, you're talking about the ozone layer, it is in the stratosphere, and that is what absorbs and scatters solar ultraviolet radiation. So if you're ever wondering about that, now you can be a little bit of a nerd and talk about it. Next, we've got our mesosphere. So our mesosphere, of course, starts just above the stratosphere and extends up to 275,000 feet. Meteors, when they come into our atmosphere, this is the layer that they end up burning up in. And as you get into the mesosphere, you're going to have a rapid decrease in temperature that gets to minus 100 degrees Celsius. So just a titch cold. After the mesosphere, we have our thermosphere. So it extends up to 500 kilometers high. And then satellites will be in this layer, as well as anytime you see the aurora borealis, that is the layer in which it is forming. So I don't know how many of you have been getting the chance to watch a lot of the aurora borealis sparks that we've been having, but yeah, now you know which layer it is. Cadet Cook, you can say that, but it just feels that way. Then we have our exosphere. So our exosphere is the upper limit of our atmosphere, extends from the top of the thermosphere, and it goes all the way to space. So that's the last barrier. That is the final frontier, if you will. I'm so sorry I said that. Are there any questions about the levels of the atmosphere before we head on to our next portion of the atmosphere? I will take this as a no, which is perfect to me. So the next part is yes, I can absolutely say the numbers for how high and how low they are again. Absolutely. So let me just go back. So our troposphere, that starts at the surface of the Earth, and then at the poles, it's going to be 28,000 feet above, and at the equator, 54,000 feet. The stratosphere will start just above that, so closer to the poles, closer to that 28,000, closer to the equator, closer to that 54,000, and then it'll go 50,000 above that. So at that point, we're at a max 104,000 feet above the Earth. Then for our mesosphere, we go from that, let's say, maximum of 104,000 feet to a maximum of 379 feet above the Earth. So stratosphere will end up going from that 104 to that 275. Or sorry, backwards. It'll go to 275 feet. Thermosphere will go from that 275,000 feet to 500 kilometers high. And then the exosphere goes from approximately 500 to 600 kilometers to where we decide space is. So for our next point, we're going to be talking about the composition of the atmosphere. So can I have you guys just tell me in the chat or raise your hand and I'll call on you what the atmosphere is made out of? Cadet Cook, you can give me one.
Hydrogen.
Hydrogen. How much hydrogen, though?
1%, I think. Or is that 18?
Less than 1%.
Oh.
All good. All right, I see nitrogen and oxygen. Nitrogen, what's the percentage of it in our atmosphere? Can somebody tell me that? You're not allowed to raise your hand in the back. Close to 80. Yeah, absolutely. And then our oxygen, can somebody else tell me approximately how much, what the percentage of oxygen is in our atmosphere? Perfect. Yeah, so we've got our about 78% nitrogen, our approximately 21% oxygen, and our 1% other gases. So for the purposes of this, water vapor is deemed as a gas. Then we've got our carbon dioxide, our argon, and things like helium. Even though water vapor is less than 1% of the atmosphere, it's still the most important component when you think about it for weather. I mean, it's kind of hard to have weather without water, as I'm sure when you think about it, you'll all kind of realize. But especially because of how versatile water is and how well it's able to change, that's why we think of it as the most important component of the fun that is weather. So next thing we're going to talk about is our temperature scales. So as I'm sure, hopefully you all know, generally we look at this within Celsius, especially within the aviation world. A long time ago, we decided that we were going to standardize things when we look at them. So having our temperatures in Celsius was one of the ways that we assisted with that standardization. And you can also take a look at it as, I don't know how many of you drive, but for example, when you are gassing up your car, the gas pump always says that the volume is corrected to 15 degrees Celsius. And you're going to see a little bit about 15 degrees Celsius and how that fits into ICAO standards later in this. So something fun. But as I'm sure you all know, water is going to boil at 100 degrees Celsius and it's going to freeze at 0 degrees Celsius. Then we've got the fun of our horizontal temperate differences. So as stated before, when talking about our different levels of the atmosphere, temperature is going to change as you go up and down through those levels. It's just math, it's just science. So there are some different things that assist in that change. The first one is our diurnal variation. So during the day, solar radiation heats the Earth. At night, you've got terrestrial radiation that occurs and the surface cools. So solar radiation, sun rays are coming down. Oh my gosh, they're heating everything up. It's great. Terrestrial radiation, that is when the heat from the Earth or the surface, because generally it holds heat better and it's going to be warmer than the air, it gives off that heat to the air, which is what cools off the surface and heats up the air above it. It's a basis of thermodynamics. If you've done any learning on that, heat likes to go to cold things. So something to keep in mind. Then you've also got our seasonal variations that cause some fun little differences in our temperature. Because the Earth's axis is tilted, the solar radiation that hits the Earth varies by the season. So, for example, as I'm sure you're all feeling right now, you're going to have stronger sun and more sun in the summer compared to in the winter. I'm sure that I'm not the only one who, if I look outside my window, it's dark already. Who doesn't love winter? Then we've also got our latitude. So the sun is more directly overhead in our equatorial regions and receives more direct and stronger solar radiation than the poles, which it receives at angles. So everywhere you go is going to have a little bit of a different sort of feeling for how much, for what the temperature can get to, as well as the weather that can affect that area. There's a reason why the equator doesn't really get snow. I don't think it ever gets snow. Then we also have our topography. So different surfaces are going to absorb that heat and that radiation better than other surfaces. So for example, land absorbs it a lot better than water because water takes more energy for it to get that heat. So land surfaces will also radiate that heat more easily. It'll hand it off to the atmosphere better, meaning that they warm faster during the day and it cools more quickly during the night. And then, of course, the opposite is true for water or more moist surfaces. So, for example, things like wet soil or like a swamp act more like water than they do land surfaces. So they take more time to get that energy and release it slower. Snowy surfaces or really light colors, whether it's sometimes crops or things like that, can reflect that solar radiation back. Dense vegetation can act as insulation, which helps with preventing that heat loss from the earth. It doesn't transfer as well. And then the greatest horizontal temperature variation happens over arid, barren surfaces like deserts and rocky plains. So the less moisture there is, the better that it takes in that energy and releases that energy back into our atmosphere. And then, of course, we've got our good friends or the enemy of any good gliding season, clouds. Cloud layers reflect large amounts of incoming solar radiation back into space, and at night, the clouds absorb the outgoing terrestrial radiation and reflect it back to the Earth. So it's really good at kind of acting as a barrier and just pushing things back to where they came from. Are there any questions, comments, concerns about the fun that is temperature scales and differences between our ability to change the horizontal temperatures? Nothing? Okay, perfect. Next point we're going to be talking about is properties of the atmosphere and ICAO standards. So before we get into that, who can tell me some of the properties of the atmosphere? I'm going to give you a little bit of time for this because I want to know what you all know. It's all good if you don't know. That's what I'm here for, to teach you. So, when it comes to the properties of the atmosphere, the first one is its mobility. So, it's the ability for air to move. It flows like water. Gases and liquids like to flow. That's part of their whole thing. So air will definitely flow and it likes to move about. Compression is another one of the properties that we like to look at when we're talking about the atmosphere. So air is compressed as it descends into greater pressure. Air ends up occupying less space. So air is really good at getting squished about because of how much space there is between the molecules. So it gives us a lot of opportunity to get some wiggle room in there. And then we have our expansion. So as air rises to lower pressure areas, it ends up cooling and expands. Cooling condenses the water in the air. That's what helps us make our clouds, along with a few other things. This is why clouds and precipitation are common in areas of rising air. And from a meteorological standpoint, it's the most important property of the air. Without that expansion and that cooling ability, we wouldn't have clouds. Makes it a lot harder to do so if we can't get an effective cooling. Who can tell me some of our ICAO standards or what ICAO stands for? International Civil Aviation Organization. Exactly. Perfect. So we have what it stands for. What are some of its standards? I'll give a moment or two for this. Altimeter setting. Yep. They definitely have some play in what we do for altimeter setting. 15 degrees Celsius at sea level. Absolutely. I'll wait and see if we can get one more and then I'll go into it. Alrighty, so for our ICAO standard, the first thing is that it's based off of sea level for North America. It's based on summer and winter averages at 40 degrees north, so latitude. With this, we have a mean sea level pressure of 29.92 inches of mercury, which is 1013.25 hectopascals. We have a mean sea level temperature of 105 degrees Celsius. In this, air is a perfectly dry gas, which means there is no moisture up in there. And of course, as we all know, unfortunately, air is always going to have a little bit of moisture. So, and then the lapse rate for this is 1.98 degrees Celsius per 1,000 feet, which means that as we increase in our altitude, our temperature is going to decrease by that amount per 1,000 feet. Any questions about the ICAO standard? Perfect. And of course, please let me know if I am going too fast. Like I said, this is something that I really enjoy teaching about, so I want to make sure that you all have the chance to effectively learn it. So next up, we are going to talk about atmospheric pressure and measurements. So the first one is our density and our temperature. So our density is the mass per unit of volume. Cold air is going to be more dense. Those molecules move slower, they're packed together, and they are generally, if you have a pocket of cold air, it's heavier and it tends to sink. I don't know if you guys have ever had this conversation with your parents, but my parents always used to tell me that if I was cold, I should go up onto one of the higher levels of the house because it was going to be warmer there. So air's gonna, that cold air likes to sink, that hot air likes to be up high. Warm air, because of that, is less dense. Your molecules are moving faster, they're more spread out, they're lighter because there's less molecules per the amount of space if you're looking at it for the same amount of space between that and colder air. And of course, it tends to rise. There isn't really a basis of, at this temperature it's warm air and at this temperature it's cold air. It's relative compared to the other pockets that are around it. Then we've got pressure gradients. So we are going to talk a little bit more about isobars later on, but can you raise your hand real quick if you have a basic idea as to what an isobar is? Okay. Good, fantastic. All right, so pressure gradients are the rate of change of pressure over a given distance measured at the right angles to the isobars. So it's perpendicular to those lovely isobars that we're going to talk about later. The steepness of this gradient depends on how close together the isobars are. So what you can also do right now, if you have the chance, is you can take a look at, you can pull up a GFA if you go to the NAV Canada website. And if you grab the one for the prairies, the GFA will have some isobars on there, and you'll be able to see how close they are together, and if there are any areas where you think there would be slower or less wind, or areas that you think it would be higher. So as when the isobars are closer together, it means that we have a steeper gradient. It's going from one pressure measurement to another one that's about 4 hectopascals difference fairly quickly and in less area, which means that the wind is going to go between those two faster because wind goes from areas of high pressure to low pressure because it wants to fill it in. So if they're close, it means that it's steep. We're going to have good strong wind. And if they're farther away, we're going to have a shallow pressure gradient, and it's going to move slower. It's going to be weaker. So, for example, if air were removed from a room, the pressure in there would decrease. When the doors open, air would rush in. In nature, the same is true. Our air is going to move from areas of high pressure to areas of low pressure. Are there any questions about that? So it's less so that it's a lower pressure because it's always going to be the same. It's always going to be the same. Give me a moment. We're going to talk. So yes, so a shallow pressure gradient does not mean that it is lower pressure. It just means that there is more area between the differences of those two of those gradients. So let's say, for example, that this hand right here is a pressure of 1044 hectopascals, and this one is 1040. So when they're closer together like this, it means that the wind's going to go faster. The airflow is going to go faster from this hand to this hand. The further away they are, it's going to go faster, or it's going to go slower from this hand to this hand. It's not so much which one is a higher pressure, it's more so which one is, it's more so how close they are together. Does that make sense? Kind of. Okay, we're going to talk more about isobars in a bit. So if you still have questions then, please let me know, and I would be happy to later on pull up or there's going to be a photo, I believe, of some isobars at that point, so I can give a little bit of a better, example. Any other questions? Alrighty. So actually, aha, a lovely, lovely photo. So even though we have our areas of high pressure and our area of low pressure here, the only thing that difference in pressure is going to do is affect how the wind moves. So if it moves north or south, east or west, whatever, that's because it always wants to go from a high pressure to a low pressure. When you've got a weak gradient here, it just means that it's going to go from our higher pressure to our lower pressure slower. It's not going to move as effectively. Compared to in these areas here where they're much closer together, we're going to go from our higher pressure to our lower pressure faster. Does that help at all? Okay, perfect. I'm happy to hear that. All right, so the next thing that we have is the Coriolis force. So air moving from a high pressure to a low pressure does not flow directly, and that's because of the rotation of the Earth. Think about it in a sense like, for example, you just finished twirling around on something. I don't care what it is. Let's say you were spinning around in an office chair, because everybody does that some days. When you try to get up and walk straight, what your body's going to want to do is go in the direction of that rotation. It kind of wants to go with it. So at that point, you're the air. You're going from one place to another, but you can't get right there because of that rotational force that's on you. So air is deflected to the right in the northern hemisphere by this force. And as a result, the airflow is actually parallel to the isobars. Anything in motion on Earth will move in a straight line if not acted on by another force. Well, and that is one of Newton's laws. Does anybody know which one of Newton's laws that is? Perfect. Yes, that is number one. An object in motion will stay in motion unless acted upon by an external force, and that includes when it comes to its direction. So, yeah, because the Earth is in rotation, it's going to cause some nice little changes to how our air moves and how other things move. So, because of that, wind doesn't blow directly from high to low pressure. The wind will blow around the low pressure counterclockwise in the northern hemisphere. And as the air tries to turn to the right, the low pressure will try to pull the air into itself, which will result in the air being deflected to the left. And around a high pressure area, air flows out and is deflected to the right. So as air goes out, It's going to go over to the right. It's going to have a fun time. And then it'll be pulled in by the left from the low pressure areas. Now there is a law, a lovely, lovely little law that we can use to tell where a low pressure area is when it comes to just being outside. So the next time you guys are out and it's windy, which I know is going to suck in the temperature that is winter, but the next time you do it, if you stand with your back to the wind, so the wind is hitting you in the back, that low pressure area is going to be on your left-hand side. And it's the opposite if you're in the southern hemisphere. But this is known by Ballot's law. And so it's just, it's a nice little way of helping figure out where that low pressure is compared to the wind. So now that's something that you can nerd out and tell your friends and say, hey, I know why the wind is going this way because there's a low pressure area to the left of me because now my back is getting hit by the wind. By Ballot's law is a really fantastic way to be able to have a better understanding of how the wind works and being able to have an idea as to what kind of things could happen with the weather because of where that low pressure area is and what's happening around it. So I think it's quite neat. Then we've got our atmospheric pressure. So atmospheric pressure is the force per unit area exerted by the weight of the air lying above that level. So of course, as you are higher in altitude, so for example, let's say you're out here in Calgary, like I am, compared to all the way over in Halifax. Halifax is a lot closer to sea level, which means that it's going to have more air over top of it compared to in Calgary because we're higher up. This atmospheric pressure is used in our altimetry, so our lovely, lovely, our altitude indicator, to indicate the altitude of an aircraft. So it likes to tell us where we are. We've got a few different units of measurement that we utilize for pressure. So in our altimeter, we like to use inches of mercury. So that's where our lovely ICAO standard of that 29.92 inches of mercury for our standard atmospheric pressure. And then on our weather maps, we like using our hectopascals, our HPA. We've got two ways of measuring pressure generally that we like to utilize within the fun of aviation. So we have our digital barometer. So this is electronic and it will display the results digitally. It does its own thing, has a good time. And then we have the aneroid barometer, which this is what's utilized within especially the gliders that we use in the Air Cadet gliding program for our altimeters. So you have flexible metal cells that are partially vacuumed, not fully devoid of air, but they have they don't have as much air in them as they could realistically, and they contract when you have higher pressure on them. So when you're lower in the atmosphere, and expand with decreasing pressure. Both of these ways can be calibrated in either inches of mercury or in hectopascals. Those are the two big ones that we're going to be worrying about when it comes to our pressure. Then we have, as I was talking about earlier a bit, station pressure. So when pressure is measured at the airport or anywhere else, if you're measuring the pressure, It is specifically the weight of the air that is above that airport or above that station as it's being measured, and that is station pressure. So it's isolated to that area and does not go against really our mean sea level pressure. Pressure is always going to decrease with height. So station at a higher elevation is going to report a lower station pressure. If this was the only measurement that we used when it comes to figuring out pressure and altitude and stuff like that, surface pressure patterns would be meaningless, as centers of lows and high pressures would always appear over areas of higher and lower terrain. So it's not very useful when you're looking at it at a bigger scale. So to filter out that elevation effect, the pressure must be normalized to some constant altitude, in which we use our good friend, the mean sea level pressure. Well, our mean sea level, and we end up with our mean sea level pressure through that. So there is also a fun little rule of thumb, because there's always rules of thumbs when it comes to aviation. So for estimating the difference in station pressure as you change altitude, for approximately every 10 feet of altitude, the pressure decreases by 0.01 inches of mercury. For every 100 feet of altitude, it decreases by 0.1 inches of mercury. For every 1,000 feet, it is 1 inch of mercury. Both mean sea level pressure and altimeter setting are calculated from the station pressure, so we do utilize it for that purpose. The mean sea level pressure is the station pressure plus the weight of an imaginary column of air between the station elevation and the mean sea level over the average using the average temperature over the past 12 hours. So as stated before, if the air over that is colder, then it means that it's going to be denser. You're going to have heavier air, more pressure, compared to if it was warmer during that average 12 hours. So it's always fun to sort of take a look at what the altimeter setting is if you're taking a look at the METARs and taking a look at historically what the pressure was. It's fun to take a look at those trends as well as seeing how the temperature changes that as well. At least I think it is. Are there any questions about station pressure versus mean sea level pressure? Give me a quick thumbs up if you don't have a question. Fantastic. Alrighty. So next up, we have our altimeter setting. So altimeter setting is the pressure that when set on the altimeter will cause the altimeter to read station elevation when it is on the ground of the aerodrome. It is used throughout the altimeter setting region of Canada, which is generally the southern half of Canada. If you haven't done, I believe it'll be in navigation that you will be talking more about the altimeter setting regions, but that I do not have confirmed in my head at this moment in time. So this altitude is obtained using the altitude obtained using the altimeter setting is called the indicated altitude, because it's what's being indicated on your altimeter at that moment in time. The altimeter setting is used during takeoff and landing and in flight in low-level aerospace. So, for example, if you are flying the Air Cadet glider, you're not going to be going all that high in the grand scheme of things. The highest you're going to be going is maybe a few thousand feet. So that's where you would use the altimeter setting. In North America, 29.92 inches of mercury is set on the altimeter for flight in the high-level aerospace and in the standard pressure region of northern Canada for all altitudes. So when you get to the territories, that's more so where they'll be using that standard pressure region. For each pressure sensed, the altitude will display, or sorry, the altimeter will display the appropriate indicated, or sorry, I know what I'm talking about right now. It'll display the appropriate ISA altitude. So yeah. So this is our fun little, a nice little demonstration of what our ISA altitude is. Then, as I said we were going to talk about earlier, is our isobars. So isobars are lines that join areas of equal pressure using the mean sea level, and it's drawn on a surface map. The value between these lines is 4 hectopascals. So it's within 4 hectopascal intervals. The lines never cross, and as you look at a map, and especially as you look at a larger meteorological map, you'll see patterns form out of these. So you'll be able to see larger high pressure pockets or low pressure pockets. So it can be a really good way to as well take a look at sort of, okay, what might be coming towards me with this weather, with the patterns that we are seeing right now in our high pressure and low pressure areas. When it comes to isobars, we've got 2 different primary ways that we kind of categorize them. So we've got a trough, which is an elongated area of low pressure, with the lowest pressure forming a line of relative minimal pressure. So it's going to be low, nice, and in the middle, and it's just extended areas. And then you've got a ridge, and a ridge is an area of high pressure with the highest pressure forming a line of relative maximal pressure. So all of them are going to be sort of just oblong areas of this pressure. Are there any questions about isobars? Once again, give me a thumbs up if you're feeling good about this. Because then we get to go on to precipitation. Fantastic. Alrighty, so now we have our good friend precipitation, which is nice to have for the most part, unless it's it ends up snowing like 3 feet, which I have my fingers crossed for everybody on this call that does not happen in the next week or so, because that would not be a fun time. But for clouds to have precipitation that will fall, there are some different factors that it depends on. So in reality, most clouds have the potential to create precipitation, but they need to have these variables met to be able to have precipitation that actually comes down to us. So you're going to have, of course, cloud droplets, drizzle drops, and raindrops are very much different in sizes. I'm sure if you all think about what a nice drizzle looks like on your windshield or on the window of your bedroom compared to a nice heavy rainfall and raindrops, you can picture the difference. A raindrop's going to be bigger because it's able to, it has more of that water that has collected in itself. So cloud droplets, because of their size, only need a weak vertical current to keep them aloft. So they don't need as much effort put in to keep them floating and staying as a cloud. Drizzle droplets have a clear, visible downward velocity, so that a light vertical current is needed to keep them up. So you don't need as much as for a raindrop, but you still need more than a cloud droplet. It's got to put in a little more effort to keeping that moisture, that formed moisture, up in the cloud. And then a raindrop has considerable downward velocity. It's got a lot more mass to it, and it'll need stronger vertical currents to keep them aloft. These vertical currents can also are actually also why, for example, if you get some nice chunks of hail, the bigger they are, the stronger those currents were within the cloud, because it gave it the chance to collect more moisture onto the hailstone. And of course, the size of the droplets vary depending on the situation in which they are formed. So different things are going to affect that size, but generally, rain droplets are going to need some more oomph to them for keeping them into the cloud and collecting more of that size to them. Then you have your intensity. So the intensity of your precipitation depends on the strength of the updraft within the cloud, as well as the cloud's vertical thickness and water content. So for having strong and big raindrops, for having those large ones that feel like they just absolutely attack the ground, you need to have stronger drafts to keep it afloat as it gains more mass. So the heaviest rainfall is going to occur with the large convective types of clouds. The more convective it is, generally, the bigger the raindrop is going to be. The vertical thickness of the cloud is important as well, because the air must be warm in order to hold lots of water vapor, and that's only possible with a lower cloud base, because, of course, as we get higher in the atmosphere, it's going to get colder. And then clouds that extend past the freezing level can produce many different types of precipitation. So that's when we get our snow grains, ice pellets, snow pellets, and our best friend, at least out here in Calgary, hail. So we've got some lovely different types of our intensity, and I do apologize if this slide is not very fun to read. So for example, if we're going between our showers, our intermittent, and our continuous, our showers are short in duration. They begin and end abruptly with a noticeable brightening of the sky between them. They fall from cumuliform cloud, though they may be embedded in a layer cloud. So sometimes it'll just be that rain that comes in and goes out and causes you a few problems here and there. With intermittent precipitation, it's not showery in character, so it doesn't have that same abruptness to it, but has stopped and recommenced at least once during an hour. So started, took a breather, and within the hour, it started up again. And then you have your continuous precipitation. So not showery in nature, but it continues without a break for at least an hour, and then falls from layer clouds. So even if it starts up pretty abruptly, if it can go on for a little bit of time before it's no longer continue to shower. And then, of course, like stated earlier, for our factors, we've got the strength of the updraft, we've got our cloud's vertical thickness. The thicker it is, the more intense the precipitation is, and then the water content. So the higher the dew point, the greater precipitation rate you will have. So if the cloud doesn't have a lot of water, it's going to run out of steam while those water droplets are forming into whatever type of precipitation they're going to be, compared to if there is more water within it, it's going to have more to gather it from. Then we've got our precipitation types. So we've got our drizzle. They're very small drops of water. They almost feel like they're floating. They're just kind of hanging out. You've got our rain, our nice large water droplets that pack a punch when they hit the ground. You've got our hail, which is a hard, transparent layer of ice covering a soft white core. I'm sure if any of you were out in Rocky this summer, you experienced some lovely hail there. It's always fun to see how quickly that can form. You've got your snow grains, which are tiny snow crystals, which have acquired a coating of rime, so a coating of frost. You've got snow pellets, which is soft white ice. So that's hail, but without that transparent layer. It didn't have the chance to go back up into the cloud because of an updraft to get that layer on it. You have snow, so your lovely classic snowflakes, nice agglomeration of ice crystals in a lovely little star shape. You have your ice prisms, which are tiny ice crystals in the form of needles. And then you have ice pellets, which is formed by the freezing of raindrops. That, of course, is different than the fun that is freezing rain, in which for freezing rain, the water is so cold that as soon as the surface tension of the droplet breaks, it freezes. Are there any questions about the fun that is precipitation? And once again, if you have no questions, give me a thumbs up. Fantastic. Alrighty, so next up, we're going to talk a bit more about our humidity. So first thing we're going to talk about is relative humidity. And this humidity, when we talk about relative humidity, it's the ratio of water present in air compared to the same amount, and compared to the amount that that same volume could hold if it were saturated. So you can think about relative humidity as looking at it when you have two sponges. They're the same size and you have one that is completely soaked. It cannot hold any more water. This is the maximum amount it can. However dry the other one is compared to it, that's the relativity of humidity it is compared to the one that is just all humid. It's all wet. Then we have our dew point, and the dew point is the temperature to which air must be cooled at a constant pressure to become saturated. So you can think about that as that sponge has gotten smaller, that relative sponge has gotten smaller. So that water, technically there's going to be more of it within the space of it. Feels a little silly, but. And then, of course, the warmer the air is, the warmer the air is, the more water it can hold. Water vapor molecules will move more quickly, which means that it's less likely to condense back to liquid. So down at the bottom here, we have a lovely little demo of showing our relative humidity. So let's say, for example, and our dew point. So let's say, for example, 10 degrees here is our dew point. At that point, we've got that 100% relative humidity. It is full, full, full. If we go to 20 degrees, for example, now at this point, we're only at 52% relative humidity compared to that fully saturated air mass we had, or example we had. And at 30 degrees, we get down to 28% relative humidity. We're going to talk a little bit more about our good friend, the dew point. So dew point is a measure of how much water vapor is in the air. A high dew point equates to a high water vapor content. The dew point temperature, which is what we commonly refer to as just the dew point, is the temperature that the air has to be cooled for condensation to occur. So for it to become fully saturated and then for it to create any sort of cloud or precipitation. So the dew point temperature is the temperature at which the air can no longer hold all of the water vapor, which is mixed in it, and some of the water vapor must condense into liquid water. So our fun precipitation. The dew point is always lower than or equal to the air temperature at the moment in time. So you're not going to see it when you look at METARs. You're not going to see it where the dew point is higher than the air temperature. It's always going to be either the same or lower. The significance of a high dew point temperature is heavier precipitation. The more moisture in the air, the more of it that ends up leaving the air, that turns into liquid water and precipitates out. This also creates a greater release of latent heat, and that's what drives thunderstorms. You've got a high heat, you've got a high moisture content, and it just kind of goes. So we also take a look at our dew point temperature and our relative humidity when it comes to being at a cadet summer camp, cadet training center, and sort of deciding what activity level you guys can go with. So if the dew point temperature is nice and high, it's above 24 degrees, and the heat's probably above 24 degrees, it's going to feel bad. It's going to be humid. It's going to be terrible. You're going to be feeling like you're just, you might as well have turned into a swamp. It's a bad time. And then as it gets lower, it gets drier, is how it feels comparatively. All right, now we are getting into our last teaching point for this. We still have one more lesson to go today, but this is our last teaching point for this. And this is atmospheric heating and cooling. So the first one is our latent heat. So latent heat is heat that is obtained by water molecules as they transition from liquid or solid to vapor. So as they go from as they change from one type of mass to another, the heat is released when molecules condense from vapor back to liquid or solid form, creating cloud droplets and various forms of precipitation. Latent heat, which is also known as latent energy or heat of transformation, is energy released or absorbed by a body or a thermodynamic system during a constant temperature process, usually a first order phase transition like melting or condensation. So first order phase being from liquid to gas or from liquid to solid. So of course, our fun changes of state, as we've probably all dealt with in our high school science classes, because science class loves this stuff. You've got our evaporation, it's liquid to gas. With the latent heat, it's either absorbed or it's needed. You need more heat, more energy to get to the state of evaporation, or to go into gas utilizing evaporation. When you have sublimation, so you're skipping the point of liquid and you're going from solid straight to gas, you're going to need more heat available to be able to do so. For condensation, you're gas to liquid, you're releasing that heat and that energy to get to a state of lower energy. Melting, solid to liquid, you have that latent heat of fusion, and so that heat you're going to need to absorb that heat, or it is absorbed. To do so, gas to solid, you're getting rid of all of that energy to skip the point of liquid. And then for freezing, our liquid to solid, you're releasing that energy once again. So if we've got a dotted line here, it's releasing that latent heat to go from that state to another. And if it's a solid line, it's absorbing heat to get to that state to another. Then we have our lapse rate. And so our lapse rate is important when it comes to also taking a look at how our liquid, or how the water vapor, is going to be changing. So the lapse rate states how much the temperature is decreasing the higher we get into the air. So it's the rate at which it does that. So we've got our ICAO standard, which is nice and snugged up between our dry adiabatic and wet adiabatic, or saturated, at a nice 1.98 degrees Celsius per 1,000 feet. I do believe that should say altitude. Thank you. Yeah, I will bring that up. Thank you very much. So our dry adiabatic, as the air is dry, it's going to lose that energy faster, which means it's going to drop 3 degrees for every 1,000 feet in altitude you go. With a wetter air mass, with that saturated adiabatic, you're going to lose less heat per 1,000 feet. So you're going to lose 1.5 degrees Celsius is how much that temperature is going to drop. The standard that we go for is our 2 degrees Celsius per 1,000 feet. And then there's our ICAO standard, which likes to be a little more precise. All right. Talking more about our atmospheric heating. All matter radiates energy in the form of electromagnetic waves. The amount of energy and the wavelengths depends on the temperature of the matter. The hotter a substance is, the greater the amount of energy emitted, and the shorter the wavelength will be. This is the main way that the Earth is heated. This radiation is a combination of visible, infrared, and ultraviolet radiation. Most of the solar radiation passes through the atmosphere freely, although some of it is absorbed by the ozone layer, and then some of it is reflected by clouds and snow. Like stated earlier, the cloud likes to act like a barrier. It'll bounce it back to wherever that radiation came from. The troposphere receives its heat from that terrestrial radiation, so from the Earth's surface sending that heat back out into the atmosphere, as well as from conduction, which is the fun of like a apologies, having a brain moment today. But conduction and convection as well are really useful for that. The heat is distributed through the troposphere by several other processes. These processes are convection, turbulent mixing, the release of that latent heat, advection, and compression. So we're going to talk about those. So the first one is convection. I don't know how many of you have a convection oven, have lived the wonderful life of having a convection oven, but it works in the same way as this atmospheric heating method does. So surface layer of air gets heated from the surface. because of that, and because heat rises, it climbs up as a convective current, which carries the surface heat upwards towards the atmosphere. So the heat's going to rise, some air is going to take over that spot that it just left, and it's going to be colder air because it's denser, and it's just going to bring that heat up. Then you have our turbulent mixing. Wind causes turbulent air motion that mixes the surface layer of air that has been heated by conduction with the cooler air aloft, which then heats it and spreads the heat upwards. So as you get a little more bumps and bruises on the earth and the wind moves that air around, that mixing and that desire of the hotter air to give off its energy to the cooler air makes both of them changes both of their temperature, but makes the cooler air warmer, and it spreads that heat as it goes. Then you have our latent heat, which we love talking about latent heat today. So water vapor evaporated from the into the atmosphere from the Earth's surface is frequently carried aloft. If it should condense, the latent heat is released. This heat, which originated near the Earth's surface in the evaporation process, is thereby distributed in higher levels of the atmosphere by condensation. So because it is changing from, because it is changing its state of matter, then it is releasing its energy and its heat. Then we have our advection warming. So air being carried from a cold portion of the Earth's surface to a warmer portion by Earth will have its lowest levels heated by conduction, and the heat will be distributed upward by convection and turbulent mixing. So get a nice little mix. It just puts it all together. And then we have compression. So this is occasions when large sections of the Earth's atmosphere subside. This would occur in the instance of, for example, air flowing down the side of a mountain range. As the air descends, it comes under increased atmospheric pressure and it gets compressed. And because of that compressing, it ends up heating up that air that has been squished on down. So things like Chinooks, for example, if you live in Calgary or you live out here in Alberta and you have the fun of, oh yay, here's just a bunch of wind and it's warm and the snow is gone, it's likely the fun of compression doing its thing in warming. Then we've got our atmospheric cooling. So atmospheric cooling is pretty important. It increases the density of the air, and when it is moist and it's cooled, you're going to get your clouds, your fog, and your precipitation. Without that cooling, it makes it a little bit harder to get weather. So we've got some different types of cooling. The first one we have is radiation cooling. So this happens at night and will seldom affect more than the lower 4,000 feet of the atmosphere. So it stays pretty low compared to how high our atmosphere goes. The temperature above that point will virtually change. It virtually will not change between night and day. So under 4,000 is where this radiation cooling is really going to take into effect. So this is just the as the heat is being released from the earth and then later on gets released from the air, it's just radiating it off, sending it somewhere else, getting colder. This does not apply to the long winter Arctic night. So further north you go around here, this isn't going to affect you. Throughout winter, the continual radiation cooling can cool the entire troposphere. So it won't just stick down to that first 4,000 feet. It goes everywhere. Then we have our evaporation cooling. So as rain falls, it will partially evaporate. The heat required for evaporation is taken from the surrounding air, and because of that, it ends up cooling it. Then we have our advection cooling. So advection is change of temperature in an air mass resulting from contact with a surface. So whether it's warm water, cold water, whatever, it is the change of this air. So advection cooling is caused by air moving over a surface with a different surface temperature, causing the air to cool by conduction from below and therefore promoting stability, which also promotes the formation of fog. So, for example, going from land over to water, with the water being colder, it ends up being cooled and is therefore more stable because it doesn't have as much energy in it. Advection warming is the opposite. So if the water is warmer than the land, the water heats the air from below, and the warmed air rises because it's less dense. So alrighty, so before we actually get to our conclusion, I have some questions. So you guys can either type it into the chat or you can raise your hand, whichever one you would prefer, but I want as many of you to answer these questions as possible. So the first question I have, what are isobars? Lines that link areas of equal pressure. Okay. And what are the intervals that they're at? Because there's a set interval that it uses. 4 hectopascals. Perfect. That's what I like to read. Alrighty. What's the composition of the atmosphere, and what are the percentages of the different parts of it? Fantastic. That's what I like to see. Yes, nitrogen is 78%, oxygen is 21%, and everything else is about 1%. What is the ICAO standard lapse rate? Per what, though? Per 1,000 feet. Perfect. And who can tell me what the saturated adiabatic lapse rate is? What about the dry adiabatic lapse rate? That's what I like to see. However, I think there might be a bit of confusion unless I am. So our dry adiabatic, because air is not as good at holding its temperature in, will lose more temperature as it rises in altitude compared to if it is wetter. So we're just going to switch those numbers around because you guys do have the right values. It's just not for the correct air mass type. So our dry adiabatic is that 3 degrees Celsius per 1,000 feet. Our wet is our 1.5 per 1,000 feet. Okay. But no, that's still good. Okay. What is one of the factors that affects the intensity of precipitation? Vertical cloud height is one of them, absolutely. What else do we have for that? Vertical thickness being our vertical cloud height, absolutely. Strength of the updrafts within the cloud, absolutely. Alrighty, so this is in fact the end of 403.01. In this class, we've discussed the foundations of meteorology, characteristics of the atmosphere, temperature, pressure, and humidity. We've talked about our ICAO standards, our various types of pressures, the changes in them and the measurements were explained, especially relating to water vapor and changes. Are there any last questions, comments, concerns with regards to this lesson? We still have one more lesson today, but are there any questions that I can answer for you guys before we go on to our next lesson? Once again, hi, hello, hello, and hi. Good evening, all. If you have forgotten my name already, or you weren't here when I introduced myself the first time, I am Lieutenant Petrie. I'm an officer with 781 out of Calgary, and I know too much about aviation and meteorology. This lesson is 403.02, which is stability of the air, and it is a 40-minute lesson, but we will take the time that we need for it today. So, for this lesson, we've got a nice good amount of teaching points. So our first one is lapse rate and stability. So we've already talked a bit about lapse rate, so we're going to get a little more in depth with that. We've got our changes to stability, our characteristics of stable and unstable air, our temperature inversions, isothermal layers, lifting agents, subsidence, and types of turbulence. So with this lesson, you're going to be introduced to, or you're going to learn about a lot of these characteristics of stable and unstable air, how stability can be modified, as well as the fun of learning about lifting agents, which will sound very similar to atmospheric heating, but there are some differences. Air stability is going to affect our weather, so having a basic understanding of this helps you understand how it will affect flying conditions, and it can help you as a potential future pilot avoid poor weather conditions. So being able to see the trends and understand them without having to look dead in the eye of the weather is a really useful skill to have. So, of course, first one we're going to talk about is our lapse rate. So, as described in the last lesson, our lapse rate is the rate at which air temperature decreases with altitude. So, a steep lapse rate, so if it loses less, or if it loses more temperature in a lower amount of altitude, that indicates unstable air because it's changing that quickly. If the lapse rate becomes steeper, the air becomes more unstable. So if it changes from, let's say, for example, it changes from our saturated wet, which who can type real quick in the chat for me what the lapse rate for our saturated adiabatic is? Or turn on your mic and say it out loud. Go ahead, Brinkhurst. Fantastic. So if we go from that to our dry adiabatic, which who can tell me real quick what that is? Fantastic. 3 degrees per 1,000 feet. Perfect. So if it changes from our wet to our dry adiabatic, we've gone from a shallower lapse rate to a steeper lapse rate because we're losing more temperature in the same amount of height that we've added. So it's going to become more unstable as we get to that point. Stable air is going to be indicated by a shallow lapse rate. So if it doesn't change temperature as much when it's going through the same when it's going through that same altitude difference, it's going to be stabler. And of course, as if the lapse rate becomes less steep, the air will end up becoming more stable. So now we have our fun of changes to stability. So as I'm sure you are probably sick of hearing now already, the stability of an air mass changes by changing the lapse rate. So for example, if you're heating from below, so you've got your daytime heating or advection, that will end up causing instability. The warmer an air mass is, the more those molecules are moving around, and the more it's going to want to run around and cause problems, like an energetic toddler compared to a very sleepy and tired toddler. When you've got cooling from below, that's like your sleepy toddler. It's going to be stable. It's not going to be running around causing a mess, causing problems. Wow, that was fast. Are there any questions about those two teaching points? Because that went by very quickly to a scary amount. If you don't have any questions, give me a thumbs up. Fantastic. Okay. Alrighty, so now we're going to talk about the characteristics of stable and unstable air. And some of these things may feel a little bit confusing, but especially when we put into your mind which one we'd maybe want more, or we'd be more interested in for gliding, for example, makes things a little bit confusing, but that's okay. So when it comes to our lapse rate, our stable air is going to be shallower, so there's going to be less changes, or the changes are going to be smaller. Whereas for our unstable air, it's going to be steep, it's going to be big changes. For our cloud type, in stable air, we have our stratus type, whereas in unstable air, we have our cumulus type. For precipitation, stable air is going to be uniform intensity, and that does include drizzle. If it's all going at the same intensity, then that's what matters. Whereas for unstable air, that's our showers. So it's going to start up and stop in a fairly short time frame, all things considered. With our visibility, in stable air, you're likely to have poor low-level visibility because you don't have as much moving around of that air, so it doesn't disrupt potential pockets of fog, for example. Whereas in unstable air, it's going to be good visibility except for in precipitation, because, yeah, precipitation kind of likes causing problems when it comes to your visibility. With your wind, in stable air, you'll have steady winds, which can change with height. Unstable air, it'll be gusty. For turbulence, in stable air, it'll generally be smooth flying, whereas for unstable air, it may be moderate to severe. So I'm going to ask you guys this question. Which do you think would you would prefer as a glider pilot? And you can either type it or you can raise your hand and I'll call you on and you can say it out loud. Cadet Cameron, why do you think you would want stable air as a glider pilot? Or any of you, why do you think you would want stable air? And then for Ashish or anybody else who says unstable, why would you want unstable air as a glider pilot? Unstable for visibility. I like that, Brinkhurst. That's not bad. Air rises, aiding the glider to gain altitude. Now, Zographos, is that more so for stable or unstable? And Cameron, because you're relying on lift aided by forward motion, you have no power, so the stable air allows more time. Okay. Thank you, Zographos. And please, if I am mispronouncing your name, let me know. Cameron, I like where your head is going with this, and some of you are going to be surprised when I say this, but for the purposes of gliding, Zographos, thank you. But for the purposes of flying, unstable air is actually what might help you out a bit more. Because your ability to stay up in the air is so dependent on your surroundings and on the areas of lift that you have around you, having that unstable air and having those pockets of lift means that you can actually increase your altitude, which also means you're increasing your airtime. So, for example, if you are doing thermaling, which sometimes you'll do that for sometimes you'll do that for either trying to beat records on altitudes that you can hit in a glider or for trying to get good distances. Having that cumulus type cloud, because cumulus type cloud, let me get my words straight. Because cumulus type clouds are formed over pockets of lift, pockets of rising air, if you've got those cumulus formed clouds, it is going to be bumpier. For a glider pilot, it does mean that you will, that if you have enough of those around and you're being careful enough with them, you will end up with more airtime and more altitude gained after your release. Does unstable air blow clouds away because of increased turbulence? So the turbulence itself can disrupt the formation of the clouds, but it also depends on where the turbulence is, because if it's more surface level turbulence, that won't affect the clouds as the higher clouds, for example. And of course, if when we're thinking about the wind blowing the clouds away, we want to think more about those isobars and how close or far apart they are, because that will control how strong our wind is compared to if it's stable or unstable air. Convection heating is absolutely an unstable circumstance that for gliding is kind of helpful. Only real danger is wind shear, which isn't common unless it's really bad. You can still get some pretty good wind shear as you get up in the air, as you increase your altitude. The wind is actually going to it'll veer and increase. And as you're going down, it'll back and decrease. So you're going to get some more, or it's likely that you'll get some more wind as you get higher up. But Ashish, did what I say make sense at all about the about unstable air and blowing clouds away? Perfect. Okay. Now, before I go on to the next slide, if you are flying power, for example, you might prefer the more stable air because of those smoother flying conditions. But especially for what we do a lot with the cadet program, which is sticking with our VFR, which who can tell me what VFR stands for? Visual flight rules. Perfect. So especially with that, it's kind of hard to use the visual flight rules if your visibility isn't great, which can definitely cause problems with trying to get training done. So within the Air Cadet gliding program, and especially for training that you guys would be doing at this point, it feels weird to say it, but you might prefer unstable air compared to that stable air. Are there any questions about that before we go on to the next slide? Give me a thumbs up if you don't. Give me a hands up if you have a question. Fantastic. That's what I like to see. Alrighty, so next up we are going to talk about temperature inversions. So there is this can change what height it ends up as, but an inversion is when the air temperature increases with an increased height. So this generally likes to happen overnight, for example, because that overnight cooling creates the inversion a few hundred feet above the ground, and that can produce significant wind shear. So as our temperature changes, and because our density will change as well, it can cause some nice little issues with with a big difference in what our wind directions are. Inversions can also form when low air gets trapped in low-lying areas. So if you've got a nice valley somewhere, you can have an inversion within that area. They also occur when warm air is lifted above colder air at a frontal surface. So when you have a nice little front area, it requires stable conditions to form, and you don't want to be soaring when there's inversions. Being that they like to happen overnight, you're probably not going to be gliding anyway, especially at this point. If you get your license through the cadet program. But because of that wind shear, because of how drastically it can change, it's a dangerous thing to potentially get caught in. So nocturnal inversions form almost every night over land. They're really quite common in winter, and there are some different ways that they are indicated. So if you have smoke that spreads out in layers, if you have poor visibility, fog, as well as layered clouds can indicate a temperature inversion. Are there any questions about that? Give me a thumbs up if there isn't. Fantastic. All right, so the next thing we are going to be talking about is our good friend, the isothermal layer. So an isothermal layer is a layer of air in which temperature is constant for some depth. So it's going to be constant for a solid height. There may be unstable conditions below that isothermal layer and then stable conditions above it. This is also not great for soaring conditions. It's often accompanied by a layer of haze at that layer, and it often marks an inversion. So you can, so if you have an area that's just nice and stuck at a spot for temperature, and even with an increase in altitude, it's not changing much or at all, really, then your likelihood is you've got an inversion somewhere beneath it or in it. Alrighty. Before we get on to our next slide, which is talking about lifting agents, can anybody tell me of anything that they think is a lifting agent or that they know is a lifting agent? Convection, absolutely. So we'll talk about this when we get to our next slide, but I think that's actually a very good segue, Cadet Cameron. So a lifting agent is it's a condition that provides lift that initiates rising currents of air. So there are, even though, for example, the heating of an air mass can cause that lifting, there are some other things as well that can push the air up, which creates lift for us to use in our flying. Does that make sense? Perfect. So we've got 5 main conditions that provide that initiation of rising air. So first one we have is convection, as mentioned before. So this is from uneven heating of different types of surfaces. So for example, if you have water and land, which one is going to heat up faster, the land or the water? Land, exactly correct. And then if you have a dark surface compared to a lighter surface as well. Something like solar panels, for example. Where I was a cadet in, we had solar panels right by where our gliding site was. And oh man, the lift you would get off of those was fantastic because they absorbed heat so well. So as the sun ends up heating the earth through its lovely, lovely radiation, the earth will radiate that heat upwards, which ends up creating rising currents of air, which is separated by areas of sinking air. There's always going to be something that has to fill back up that area that the that the rising air, the warmer air just left. So the cold air is going to take over that space. And by taking over that space, it puts itself into a situation of being warmed up, which means that it rises, and then its buddies who are colder than it come into the spot. So as it reaches a certain height, it might not be or as it reaches whatever height ends up being it on that day within those circumstances, and it cools, it'll come back down, sort of creating a cycle. And that downward movement of air is known as subsidence. So you've got your convection and your subsidence. Then you have your orographic lift. So us out here in Alberta, love a good orographic lift. BC as well. The amount of gliding that utilizes orographic lift is fantastic, and it does very much affect our weather. So when air moves up a sloping terrain, such as a mountainside, for example, it's going to keep going up. It's going to just keep doing that. And if the air is unstable, it will continue and it will increase the amount of lift that is provided from that. So as it goes up, it kind of just keeps going up. And eventually it'll come back down, but it wants to keep going up. Then we have our frontal lift. So when we have either a cold front or a warm front, whatever it may be, when you've got those two different air masses that meet, or multiple different air masses, which does sometimes occur, the warmer air is forced aloft, so it's forced up by the advancing or receding wedge of colder air. So it's going to go up because it's less dense than the cold air. The cold air is going to undercut it. It's going to just go up. Because of it going up means that you've got lift. Simple as. So when you have frontal lift via a warm front, you've got the warm air that advances onto a retreating cold air mass. The warm air ascends over the cold air in a nice, long, gentle slope. It overtakes the cold air mass. The warm, rising air cools. It ends up condensing, and it forms clouds with steady precipitation. So how many of you are aware of the acronym CCANs or CCANs when it comes to clouds at a warm front? Just give me a quick thumbs up if you are, and if you're not, then this gives me a chance to teach you a little something else. So if you're ever wondering, or you might not wonder this, and that's okay, you're allowed to be a little less nerdy than I. If you're ever looking out and going, those are some funky clouds, I wonder what that could be. CCANs is a method of determining a warm front by the types of clouds that end up arriving because of that frontal lift. So at the top, you'll have cirrus clouds, so some nice, good wispies just hanging out. You'll have cirrostratus clouds. You'll have altostratus, and then you'll have nimbostratus clouds. So cirrus, C, cirrostratus, C, altostratus, A, nimbostratus, N. CCANs. I remember my first summer teaching ground school for Brandon, having one of my cadets run up to me after a day out on the field and very excitedly inform me that he saw the CCANs and he understood what I meant. So now you know. If you're ever like, that's a funky little pattern of clouds, now you know it's because of a frontal lift. And because of a warm front. Then we have our frontal lifts via cold fronts. So massive cold air advances on a warm air mass. This cold air undercuts the warm air, so it just pushes right under it. You can think of it like a bulldozer almost. It just cuts right under it and picks it up. That forces the warm air to rise sharply. It's going to go a lot faster in rising compared to that nice steep slope of the warm front. When you get a cold front, you end up with with a few different clouds, but the two more prominent ones are going to be your towering cumulus and your cumulonimbus. And if you see those two clouds, can anybody tell me what you would probably expect to see from that as well, or that you might end up seeing? Precipitation? Absolutely. There's a thunderstorm. Absolutely. You've got something mean like that that's just getting pushed up and developing. You're gonna you have the chance of getting some nice, mean weather. And you're gonna get heavy precipitation with that too. Then we have the fun of mechanical turbulence. So mechanical turbulence is specifically friction between the air and the ground, and it's sometimes known as eddies. So you might hear the term eddies a few different times when it comes to the movement of fluids. If you canoe or anything like that, when your paddle goes into the water and you're moving, but the paddle's just standing up in it, the water that kind of flows around it and makes those little whirls, those are eddies. So if you're ever like, I want a visual representation of that, there's one for you. This is generally made more severe by irregular terrain and man-made obstacles. So when you have the fun of a lot of different buildings of different heights, if you have terrain that's kind of all over the place, there's no set standard, it's not all flat, but you've got 17 different altitudes that are in that area, then you're going to get more severe mechanical turbulence. And then it's usually confined to the lower few thousand feet above ground level because for the most part, it's happening where there are these things that can cause problems that end up being boundaries and push it out of the way. And it's only going to go so much higher than that. Then we've got convergence. So convergence, you can see this a lot when you have air moving from that high pressure to that low pressure, as it loves to do. It likes to go hang out with the low pressure groups. So the air converges and it meets over the center of the low pressure, and you can only fit so much air in one spot. You can think of it like as a really packed concert almost. At some point, you're probably going to have people who end up on top of the crowd in some way, shape, or form. The air is doing that. The air there's too much of it, it's in the way, it's causing problems, it ends up getting pushed up so that it gets out of the way of the lowest part of the low pressure area. Because it still wants to be in there, it just can't be down there. Are there any questions, comments, concerns about lifting agents? Give me a thumbs up if you're feeling good about it. Perfect. That's what I like to see. Alrighty. Next up, we have subsidence. So we talked about this a little bit as well already when it came to the, I know what words are right now, when it came to convection. So subsidence is just the word for downward moving air. Doesn't matter if it's happening with convection or not. If it's downward moving air, it is known as subsidence. So some weather systems are favorable for the development of sinking air. This occurs in anticyclonic pressure systems or in air flowing down down a mountain range. So as air descends into regions of increased atmospheric pressure, it is compressed and warmed, and as a result, the temperature rises. Then we're going to talk about some types of turbulence. So convection, just like with it being a lifting agent, it can also be a type of turbulence. So it's also sometimes referred to as thermal turbulence, and it likes to happen on hot, sunny days when the sun heats the Earth's surface unevenly. You get isolated convection currents that are set into motion, and this causes turbulence. So if you have smaller pockets and areas of this convection, then because when you're going through it, it's not as steady and stuck together, it's going to be turbulent. It's going to be a bouncy ride in that. And you will find that as we go through our types of turbulence, it's gonna sound a lot like our lifting agents, because unfortunately with lift you're also going to get sink. You can't have one without the other, which means that there's, especially depending on what kind of aircraft you're using or how you're going through it, you're gonna have some turbulence. It's pretty well inevitable, unfortunately. Then we have our mechanical turbulence. So once again, sometimes referred to as an eddy, it's the friction between the air and the ground. Irregular terrain, man-made obstacles will cause severe eddies. So the air is going to go up. Something has to fill the spot that it left. As it goes up, it's going to condense. It's going to cool down. It's going to come back down. It's just a cycle. All of these are just cycles. Unfortunately, you can't have one without the other when it comes to lift and sink. Then we have our orographic turbulence. So you can use orographic lift to fly. There are some glider pilots who love to use that because the amount of lift you can get from it is really quite fantastic. It is a little bit more dangerous, but it's a really quite neat thing to be able to do. So it's known as mountain wave or rotor turbulence. Turbulence can be expected on the windward side and over the crests of the mountains along the downward slope. So on the side that the air is pushing up on and the side that the air ends up going down from. At the top of these, because you have all of that air that is being pushed up, and as it gets higher, it cools and it condenses, you end up getting rotor clouds with that. So rotor clouds will end up forming at the sort of peak of where where that lift is, and it will follow down it'll follow kind of perpendicular to the mountain ranges. So you want to make sure that you're avoiding those rotor clouds, as well as the strong downdrafts that happen on the lee side, aka the downward slope, the non-windward side of the mountain. Areas with the most intense turbulence are associated with mountain wave. So you got to be really careful with that if you ever have the opportunity or the chance or decide to use orographic lift for flying. If you do end up deciding to do this, because you are a thrill seeker or it's available or you just think it's neat, you want to approach the mountain at a 45-degree angle, because at a 45-degree angle, it means that it can't just shove you into the mountain, which is a little scary to think about, but it's a safety thing. The severity of the mountain wave, or the orographic turbulence, is dependent on the strength of the wind, its angle to the range, and the stability of the air. The most severe conditions are created in strong airflows that are blowing at right angles to the range, so exactly perpendicular, and in very unstable air. And then, last but not least, we have our good friend wind shear. So wind shear is any marked change in wind speed or direction with height that produce local areas of turbulence. So it's not going to be a huge area, it's just going to be within a set area. When the change in wind speed and direction is great, quite severe turbulence can be expected. The bigger the change, the more drastic it's going to be, and turbulence is just a nice big old change. You have, if you have low level wind shear, which you see fairly often with thunderstorms, that occurs because of gust fronts and downbursts. And gust fronts and downbursts are going to be covered more in a future meteorology lesson, but I think they're very neat, and I hope you guys will too when it comes to that. And wind shear is a primary cause of turbulence at higher levels. Alrighty, now it's time for some confirmation. So, what would be the better situation for having the most stable environment? Having a warmer surface or a colder surface beneath a pocket of air? So, if you think that a warmer surface is what you want, I want you to give a thumbs up. If you think a colder surface is what you would want for more stable air, I want you to give me an applause. I want you to give me those hands clapping. Oh, fantastic. And can somebody tell me why why the colder surface would do that? And feel free to either, you can turn on your mic. I'm happy to hear voices, so it's not just me talking, or you can type it into the chat. So yes, 100% correct. For stable air environment, you're going to want that colder surface. When you have warmer surfaces and you get that lifting agents and that heating of the air, you, as stated before, with lift, you get sink. So if you want to have something stable, you want to make sure that you're not doing changes in the temperature, or at least any changes that you're doing are making it denser and a little bit harder to just decide to run around screaming. All right, next up, tell me, what's an eddy and where are they usually found? Friction between air and uneven surfaces. Absolutely. Mechanical turbulence over uneven terrain. Absolutely. Where found near man-made obstacles like buildings and other uneven surfaces. Absolutely. If we were to give a potential height range for about how high it can go in the atmosphere, what is the height range? First few thousand feet. Absolutely. Good. It's nice to know that you guys are listening, paying attention. Alrighty. If you have a steep lapse rate, what does that mean? Unstable air. Perfect. Alrighty. What is subsidence? Air that is moving downwards. Absolutely. So subsidence, if this helps you think about it, sink is subsidence. So if the air is moving downwards, that's subsidence. Nicely done, you guys. All right. What are the 5 lifting agents? If you're going to answer this, type out 1 or 2 of them, and I want to see if there are any ones that people forget about. Convection and frontal lift, absolutely. Orthographic lift, fantastic. Alrighty, so we've got 3 of our 5. There's number 4, convergence, absolutely. And we're missing 1. Eddies, which are also known as mechanical turbulence. Fantastic. All right. Convergences are converging towards the center of what type of pressure? Low pressure, absolutely. Air is going to flow from our high pressure to our low pressure. Because of that, our convergences are going to happen in our lower pressure areas. Fantastic. Okay. Heating from below causes what? Unstable air, absolutely. What's an isothermal layer? Layer of air where temperature is relatively changed. Okay. And where can you, is there another type of thing that we've talked about in this lesson that you're likely to see with an isothermal layer? Yeah, you're likely to see some turbulence, especially below the isothermal layer. A transition, okay. There's a word I'm thinking of, and it starts with a correction. An inversion. Fantastic. Absolutely. Alrighty. And as a pilot and as a potential future pilot, why should you be aware of areas of turbulence? Could affect flight performance, sometimes even making you fall out of the sky. Absolutely. Cadet Cook, can I have you explain what you mean by that? I know what you mean by that, but can I have you give me an explanation real quick?
Basically, your wings or your aircraft, just too high a G tolerance on the wings, and the wings basically fold in on each other. And then you fall out of the sky.
Yes. So, it can cause problems if it's severe, can throw things around the cabin, affect flight performance, and damage the aircraft. Absolutely. So, depending on the strength as well of the updraft or the downdraft, it can overcome the structural integrity of the aircraft. And aircraft in their different spot, the different areas of the aircraft can only handle so many G's on it. It can only handle so much of that. And especially if you do go on glider, that is something that you will find out what its tolerances are for that. So you really don't want to put yourself into a situation where you can get into that problem outside of your control. Okay. And I have two more that aren't on here, but I want to know how much you all remember before we finish off this lesson. So, give me the characteristics of stable air. And give me, if you're going to answer, give me two characteristics. I do not recommend trying to turn the Schweitzer 233A into a coarse air, as fun as that may sound. Poor visibility, constant wind speeds. Absolutely. Stratus clouds and poor visibility. Yes, yes, yes. I would also like my wings to stay intact personally, but if they're designed in such a way that they can just fold up and have a good time, then I'm okay with that too. Alrighty, so we've got stratus clouds, poor visibility, constant wind speeds. What else are characteristics of stable air? I know you all can do it. We are steady winds that can change with height. Absolutely. Uniform precipitation. Absolutely. So we're generally smooth flight. Yes, 100%. And we are missing one different characteristic. I'll give a hint. What does our lapse rate look like? when it comes to stable air? Shallow lapse rate. Absolutely. Okay, now let's flip the coin. What about for our unstable air masses? What do we see with those? What are our characteristics? Gusty winds, yes. Severe turbulence, absolutely. Turbulence can be moderate to severe, but yeah, severe turbulence is definitely a characteristic. There's some of you I haven't heard from yet. Let's see it. Oh, Cameron, it looks like they've got everything. So we've got a steep lapse rate, cumulus type clouds. We're going to get showering rain. Good visibility, except if it's in precipitation. Our winds are going to be gusty, and our turbulence may be moderate to severe. Alrighty, fantastic. So, oh, I guess there was one more question because there isn't a conclusion slide on here. But let's say, for example, glider pilot is circling at 2,000 feet above ground level and sees a layer of haze 200 feet above them. What could that mean? What does that mean? Means that there is an isothermal layer above them, absolutely, or an inversion. Yeah. So that can mean that at that 200 feet above, there can be either an inversion or an isothermal layer. So you are both correct. Stable air above, absolutely. And if it's stable air above, then what could that mean for your soaring and lift conditions? And then what might happen with your visibility when you get to that point as well? I know you all have the answers to this. You've done a very good job tonight. So that's all I've got left for you. With this, with this layer of haze, what's going to happen to your visibility and what's going to happen to your soaring or lift conditions? Don't make me pull out the Jeopardy music. Low visibility, absolutely. Your visibility is going to decrease as you get into that. Oh, absolutely. So if you know that you have stable air above this layer of haze above this isothermal layer or inversion, what will that do with your soaring or lift conditions? Are they going to be good? Are they going to be bad? Are you going to want to stay up there? Bad lift. If it's stable, you're not going to get any lift. If you get any, it's going to be very minimal. Not optimal conditions because the air isn't moving. Fantastic. And of course, I do apologize. I have one more question from you guys. We talked about isobars. We talked about isothermal layer. What does iso mean? Isolated isn't bad. I like that mentality. So when we look at it in meteorological terminology, ISO is based out of Latin terminology for same. So it's the same range or it's the same temperature. ISO. Alrighty, so in this class, we have discussed atmospheric stability. As future potential pilots, it's important to understand the stability of the atmosphere in order to anticipate what type of conditions you might have to handle when you are flying. Once again, I am Lieutenant Petrie. Thank you so much for coming in tonight. I hope that you have learned something tonight. Please give me a little thumbs up if you did learn something. I always love to hear if you did. If you have any questions, comments for me as an instructor, any concerns, please let me know. I am always looking for feedback. If I can't improve, what am I doing as an instructor? And otherwise, that is the end of our lessons tonight. I will be sticking around on Teams, so if you have any questions, you're doing any studying, and you're like, hey, something doesn't click in my brain for this, feel free to reach out to me. And otherwise, I hope you all have a fantastic night. Stay warm and happy holidays.